Long before quantum mechanics and the modern periodic table, before the discovery of atoms and electrons, and even before Mendeleev, chemists already knew enough about how matter functions to say that elements exist and to isolate around 60 of them. They knew their masses, whether they were a gas, a liquid, or a solid at room temperature, and importantly, they knew quite a bit about their chemical behaviors. For instance, they knew that lithium was a highly reactive soft metal that combines with chlorine to form a salt. Beryllium would bond strongly to oxygen, or 2 parts of chlorine. Boron would combine with 3. Carbon combined with 2 parts oxygen or 4 parts hydrogen, nitrogen to 3 parts, oxygen to 2, and fluorine to 1. And both of these were reactive enough to start fires. The next known element was sodium, a highly reactive soft metal that combines with chlorine to form a salt. Magnesium would bond strongly to oxygen or 2 parts of chlorine. Aluminum would combine with 3 parts. Silicon combined with 2 parts oxygen or 4 parts hydrogen. Phosphorus to 3 parts, sulphur to 2, and chlorine to 1. And both of these were reactive enough to start fires. So if you get the feeling that I'm starting to repeat myself, congratulations, you too might have been a 19th century chemist with a controversial hot take. In the 1860s, both Alexandre Charcot in France and John Newlands in England noticed the repetition of chemical properties, or periodicity, when the elements were arranged according to weight. Neither were taken very seriously, and Newland's paper was ridiculed and rejected by England's Royal Society. Later that decade, German chemist Lothar Meyer and then finally Dmitri Mendeleev produced their own tables of elements arranged according to their weight and placed line breaks to show their periodic behavior. Mendeleev is credited because A, his was published more widely, and B, he made some pretty bold predictions that ultimately came true. He also initially denied the existence of the noble gases after their discovery because he did not predict them. Now, this is far from a complete summary of the interesting story behind the discovery and classification of the elements. And don't get me wrong, compiling large amounts of information onto an easily usable form is a truly tremendous achievement. But noticing periodicity doesn't do much to explain the periodicity. For that, we really need to know about electrons and orbitals, information they didn't have back then. Now, we've seen how the nucleus is only a tiny fraction of the size of the atom, and how electrons are only stable around a nucleus when they form orbitals, 3-dimensional spaces defined by 4 quantum numbers. What we haven't yet talked about is how those electrons interact with each other. Electrons are all negatively charged, so what happens when you start putting them near each other in the same orbitals or on the same energy level? You'd expect them to repel one another. And they do. Keeping electrons separated partly explains the size, shape, and appearance order of the orbitals. But there are other quantum effects that actually stabilize a set of electrons when they complete orbitals, or a full energy shell. The more complete the electron configuration of an atom, the more stable the atom. And this chemical stability is most obvious in atoms whose nuclei hold the right number of protons to exactly balance the number of electrons needed to complete a full energy shell. These are called the noble gases, and they're on the rightmost side of the periodic table. This means that they have a neutral charge and can only become less stable or more reactive if they give up, share, or take on extra electrons. Noble gases were late to the periodic party because, without charge or reactivity, no one knew how to look for them. In fact, helium was discovered in the sun before it was ever discovered on Earth. Next, let's look at some highly reactive elements and think about how their observable chemical behaviors are determined by their electron configuration. Electron configurations that are only 1 or 2 electrons away from completing a shell become much more stable by gaining or losing those extra electrons. We said earlier that lithium and sodium react strongly with chlorine to make salts. Comparing the electron configuration of lithium and sodium helps us understand their periodic nature. Both have 1 more electron than a full shell noble gas. Helium +1 for lithium, and neon +1 for sodium. So for lithium and sodium, giving up that one valence electron happens easily and quickly, which is just another way of saying that it's highly reactive. As for chlorine and the other atoms in its group, it is only one electron away from a full shell, but in the opposite direction. If it takes one more electron, it completes the shell and becomes more stable. And this is also true for fluorine or bromine. So these elements are highly reactive because they will take one more valence electron quickly and easily. So if sodium becomes more stable when it gives up an electron, and chlorine becomes more stable when it takes an electron, now we can start to understand how these two highly reactive elements can combine to make a highly stable salt, sodium chloride, or table salt. Understanding electron configuration also allows us to predict the behaviors of elements when they combine into salts and molecules, just by looking at their placement on the periodic table. Take strontium and fluorine, for example. How might they combine? Strontium has 2 more electrons than its nearest complete shell, krypton, and fluorine only needs 1 electron to complete its shell. So strontium can supply enough electrons for 2 fluorine atoms, and we end up with strontium fluoride salt, SrF2. Now that we can see how chemical behaviors emerge from the interplay between nuclear charge and electron configuration, we can start to justify periodic trends in the elements, like electron affinity, or how much more stable an atom gets when it takes an extra electron. Ionization energy, the energetic cost of giving up an electron. Or electronegativity, how strongly an atom pulls electron density towards itself inside a chemical bond. It also hints at why some elements are toxic, like arsenic, whose chemistry is similar enough to phosphorus to take its place and disrupt important biological functions. Or how radium can displace calcium to weaken teeth and bones, destroying tissue with chemistry and radioactivity. Finally, I mentioned in our last video that electron configuration only partly explains why mercury is liquid at room temperature. In its neutral electron configuration, it has a complete set of 6s, 4f, and 5d orbitals. Enough complete orbitals that it doesn't gain much more stability by sharing electrons. However, if that were the only important factor, then its melting point would still be somewhere around 80 degrees Celsius. Low for a metal, but still solid at room temperature. We've seen how imperceptibly small atoms are, yet the mercury atom is large enough and the pull of its 80 protons is strong enough that its electrons start to approach the speed of light, and we actually have to account for relativistic effects. Some of the electron energy is being converted into mass, making those electrons heavier, and this in turn pulls the d orbitals closer to the nucleus and stabilizes the atom more deeply than the same electronic configuration does in zinc or cadmium. The added stability makes mercury far less likely to share its electrons, and that leaves the metal with such weak bonds that it melts into a liquid of loosely held atoms somewhere around -39 degrees Celsius. Mercury is therefore a nearly noble example of how abstract concepts like subatomic particles, quantum mechanics, and relativity theory really do affect the behaviors of everyday materials and molecules. We'll hear more about bonding atoms into molecules next week.